About 14 billion years ago, something impossible happened. The universe exploded from a spot smaller than the tiniest particle, creating time, space, and everything that exists. But here's what will shock you. Scientists today have shown the Big Bang wasn't where it all started. Something much weirder came before it. Not empty nothingness, but a quantum world full of hidden energy. A place where the rules of physics were being formed. We're going on a trip through falling realities, endless cycles of rebirth, and a finding that emptiness might contain the most powerful thing we can imagine. If you love the content, hit that like button and subscribe to the channel. Let's begin. Picture the darkest spot in space you can think of. No stars, no planets, no light, just pure emptiness going on forever. Now get ready for what scientists found. That emptiness is actually fake. When quantum scientists look at the vacuum with their best tools, they found something amazing. So-called empty space is full of invisible energy. Think of the ocean on a calm day. From far away, it looks smooth and still. Get closer, and you'll see tiny waves, quick movements appearing and then vanishing. The quantum vacuum works the same way, except these waves are unseen energy fields everywhere all the time. This finding is real science, repeated in labs around the world. The vacuum has what scientists call zero-point energy, the lowest possible energy level that still has real force. You can't take it out, you can't turn it off, it's woven into the fabric of reality itself. Here's where things get weird. This energy doesn't just sit there doing nothing, it shapes our universe. When scientists put two metal plates very close together in a vacuum, they get pushed toward each other by this invisible force. Scientists call this the Casimir effect. It's been measured precisely. The vacuum between the plates has less energy than the vacuum around them, creating an imbalance that makes real physical force. This finding means what we call nothingness has structure. It has properties. It can be measured, changed, and studied. Old thinkers from Greece believed taking all matter from a space would leave absolute nothingness. They were wrong. Modern physics forbids it. The results shake up our understanding of existence. If the vacuum has energy, then nowhere in the universe is truly empty. Every bit of space has this basic hum of quantum motion. When you wave your hand through air, you move through an ocean of invisible energy that existed before the first stars lit up and will last beyond the final one's death. But measuring this energy created a problem that haunts physicists today. Reality hides secrets where nothing meets everything. When they calculated how much energy the vacuum should have based on quantum rules, the numbers exploded. The predicted value came out 120 orders of magnitude bigger than what we actually see. Imagine predicting someone weighs 10 pounds, then finding out they actually weigh less than one atom. The gap is that enormous. This crisis shows something deep. Our understanding of what nothingness truly is remains incomplete. The vacuum hides mysteries that might explain where everything came from. Scientists proved empty space has energy, but the puzzle of why it has exactly the amount it does stays unsolved. What happens when this quantum foam gets disturbed? The quantum vacuum doesn't just hold energy, it creates matter. Right now, in the space between your eyes and this screen, particles appear from nowhere. They exist for a tiny moment, then disappear back into the void. Scientists call them virtual particles, and their existence has been proven through experiments measuring their effects with amazing precision. Here's how they work. Energy and matter can swap places. As Einstein showed, the vacuum has energy, and that energy constantly changes. For the briefest instant, A change becomes big enough to split into a particle and its antimatter partner, an electron and positron, for example. These pairs pop into being, survive for a time shorter than we can comprehend, then crash together and destroy each other. The energy goes back to the vacuum. The cycle repeats endlessly. This happens trillions upon trillions of times each second in every bit of space. The vacuum isn't calm. It's a violent storm of creation and destruction happening at scales far below anything we see directly. Yet we know these virtual particles are real because they leave marks. In the 1940s, physicists noticed something odd about hydrogen atoms. The energy patterns of electrons orbiting the nucleus didn't perfectly match predictions. The difference was tiny but present. After careful investigation, they realized virtual particles were responsible. These ghost particles briefly interact with the electron, changing its energy by a measurable amount. Scientists call this the Lamb shift, proving the vacuum isn't dormant. It's alive with quantum activity. The proof gets even more convincing. Virtual photons, light particles blinking in and out of existence, create something called vacuum polarization. They temporarily shield the electric charge of particles, affecting how forces work at quantum scales. Without virtual particles, the math of quantum physics would fall apart. They're not extra, they're essential. Think about what this means for the question of nothingness. If the vacuum spontaneously creates matter even for microseconds, then complete nothingness becomes forbidden. Nature refuses it. The universe has a baseline chaos level built into its foundation. But here's the disturbing part. If virtual particles can appear from the vacuum for tiny time fractions, what stops a larger change from happening? What blocks the vacuum from creating something permanent, something that doesn't vanish? The answer involves a principle making nothingness even stranger than we can imagine. In 1927, a German physicist named Werner Heisenberg discovered a rule that shattered our common sense understanding of reality. It says you cannot know both the exact location and exact speed of a particle at the same time. The more accurately you measure one, the less you know about the other. This isn't a limitation of equipment, it's a basic feature of nature. The universe itself prohibits certain information from existing together. Now apply this to energy and time. The uncertainty principle also says that energy can change wildly, as long as it happens fast enough. The shorter the time span, the bigger the energy change nature permits. This explains why virtual particles exist. The vacuum borrows energy to create them, then pays it back so quickly that the universe's books balance. Here's the vital insight confirmed by decades of experiments. The uncertainty principle ensures the vacuum can never reach complete stillness. Changes will always happen, forever. Quantum uncertainty makes perfect silence impossible for all time. You cannot have a state of perfect nothingness because that would require knowing the exact energy at an exact moment, which nature forbids. Imagine photographing a hummingbird's wings in flight. Your camera captures blur because the wings move too fast. The quantum vacuum behaves similarly, except instead of motion blur, you get energy blur. The vacuum fizzes with possibilities, never quite settling into calm. This has huge implications. Before the universe appeared, if there was ever a state of real nothingness, the uncertainty principle would instantly destroy it. Quantum changes would emerge. Energy would spring forth. The void would become unstable. Scientists measure this instability in labs when they cool systems down to temperatures near absolute zero, the coldest possible temperature. Quantum changes become the only movement left. Atoms still tremble. Fields still move. You can remove heat, remove particles, remove light, but you cannot remove the quantum uncertainty keeping the vacuum restless. This isn't guesswork or philosophical thinking. Teams of physicists have detected these changes directly by studying how light behaves in carefully controlled experiments. They've measured the vacuum's random electric fields affecting electrons. They've witnessed the spontaneous release of photons from atoms triggered by vacuum changes. The evidence is overwhelming. The uncertainty principle creates a paradox when we think about the origin of everything. If nothingness cannot exist because quantum laws prevent it, then something has always existed. Either the universe lasts forever, or it came from a quantum state that was never truly empty. But there's a third option that sounds like fiction, yet might be confirmed reality. Imagine standing on frozen water. The ice looks solid, feels secure, but below the surface the water runs warmer than expected. The ice sits in an unstable arrangement waiting for the right trigger to collapse. This is what physicists call a metastable state. Something appearing stable, yet not truly at its lowest energy. The vacuum of space might be exactly like that frozen surface. According to quantum field theories confirmed through particle accelerator data, the vacuum can sit in different energy states. There's a true vacuum, the absolute lowest energy possible, and false vacuums sitting at higher energy levels but remaining stable for long times. Our universe might currently sit in a false vacuum, and that terrifies some physicists. Here's why. A false vacuum is metastable. It can suddenly decay into a true vacuum state if the right quantum change happens. When that occurs, a bubble of true vacuum appears and expands at light speed, transforming space itself. Everything caught in the expanding bubble undergoes restructuring. Physical laws change. Matter as we know it stops existing. Sounds apocalyptic, but flip the viewpoint and you get something remarkable. What if the universe itself started as exactly this kind of event? What if before our bang, there was a false vacuum that decayed into our reality? This theory has mathematical backing through something called the Wheeler-DeWitt equation. It describes how quantum states evolve in the context of gravity and cosmology. Researchers in China released work in 2014 showing that solutions to this equation allow a microscopic bubble of vacuum to appear spontaneously from quantum changes. Under specific circumstances, this bubble doesn't collapse. Instead, it inflates, expands, and creates a universe. The false vacuum before our cosmos would have been unimaginably tiny, smaller than an atom, possibly as small as the Planck length, which measures 10 to the negative 35 meters. At that size, space itself becomes grainy, and quantum mechanics controls everything. The normal rules about cause and effect break down. Events can happen without prior causes. Changes can create structure from randomness. This is confirmed physics at quantum scales. We see it in particle physics experiments constantly. Applying it to the universe's origin requires a leap. But it's a leap based on established science. The metastable false vacuum gives us a picture of pre-bang reality. There was no swirling cloud, no primordial substance, no time moving forward. There was only a quantum state hovering in an unstable arrangement, waiting for the change that would create everything. How do we know this quantum energy does more than just exist? Energy has mass. It warps space-time, and the vacuum's energy is no exception. Einstein's equations of general relativity tell us that both mass and energy create gravity. A ball of gas creates a gravitational field. So does a light beam. So does the vacuum's energy. Despite being spread across empty space, this prediction has been tested and confirmed in multiple ways. The vacuum energy shows up as what Einstein called the cosmological constant, a number describing how much energy lives in each cubic meter of empty space. For decades, scientists assumed this constant equaled zero. They were wrong. In 1998, two astronomer teams made an observation that shocked the physics establishment. They measured distant supernovae, exploding stars serving as cosmic distance markers, and discovered something impossible. The universe's expansion is speeding up. Galaxies are flying apart faster now than they did billions of years ago. Gravity should slow down expansion. Matter attracts matter. The universe should be slowing, possibly even shrinking. Yet the data showed the opposite. Something was pushing space apart. The only explanation fitting the math is vacuum energy. Empty, space holds a small but non-zero amount of energy density. And this energy has a strange property. It creates repulsive gravity. Instead of pulling things together like normal matter, vacuum energy pushes them apart. The more space expands, the more vacuum gets made, which creates more repulsive force. It's a runaway process. Scientists call this mysterious component dark energy, and current measurements show it makes up roughly 68% of the total energy in the universe. Think about that. More than 2/3 of reality comes from the energy of nothingness. Regular matter, stars, planets, gas, everything visible, contributes less than 5%. This discovery revolutionized cosmology. The vacuum isn't a passive stage where events happen. It's an active player shaping cosmic evolution. It bends space-time. It affects light's paths. It determines whether the universe will expand forever or eventually collapse. The measurements have been refined through multiple satellites and telescope surveys. The Planck satellite mapped temperature variations in the cosmic microwave background and confirmed the dark energy amount with incredible exactness. Ground-based telescopes measured how galaxies cluster and found perfect agreement. Independent methods converge on the same conclusions. Empty space wields power, real, measurable, universe-shaping power. And this raises a staggering question. If vacuum energy can dominate the entire cosmos today, what could it have done in the first moment of creation? The answer leads us to the most crucial event that happened before our bang. Everything you've been taught about the Big Bang needs revision. The hot compressed fireball that forged atoms and released light across space was not the origin. It was the result of something else, an event called cosmic inflation. Inflation theory, developed in the early 1980s by physicists including Alan Guth and Andrei Linde, describes a phase of exponentially rapid expansion that occurred before the conventional bang. During inflation, the universe doubled in size repeatedly in an incomprehensibly brief interval. We're talking about expansion exceeding light speed, surpassing anything physical laws normally permit. Here's the key point confirmed through observation. Inflation solves problems the standard bang model cannot. The universe shows remarkable uniformity. Galaxies separated by billions of light years have identical temperature, identical density, identical properties. How did regions of space that could never have communicated become so alike? The old model had no answer. Inflation provides one. If the universe started much smaller than expected, then inflated to enormous size in a fraction of a second, those distant regions were once close enough to reach equilibrium. They were neighbors. Then inflation stretched them across opposite edges of the observable cosmos. The proof comes from the cosmic microwave background. Ancient light released 380,000 years after our bang. When scientists mapped this radiation across the sky, they found tiny temperature variations matching inflation predictions with stunning precision. The pattern of hot and cold spots looks exactly like what you'd get if quantum changes during inflation were stretched to cosmic proportions and imprinted on space itself. But here's what makes inflation revolutionary for understanding. Before it happened, the universe was cold and empty, not hot and compressed. The inflationary period was driven by vacuum energy, the same type we discussed earlier. This vacuum energy caused space to expand exponentially, doubling the universe's size every microscopic fraction of a second. Think about a chessboard with coins doubling on each square. One coin, then two, then four, then 8. By the 40th square, you'd have billions. Inflation involved at least 80 doublings, possibly hundreds. A region smaller than a grapefruit expanded to a size larger than the observable universe. All in less time than light needs to cross an atomic nucleus. When inflation ended, the vacuum energy powering it didn't just vanish, it transformed. The energy dumped into space, creating a flood of particles and radiation. This transformation was the bang you know. The heat, the compression, the primordial soup of matter, all came from the decay of the inflationary vacuum. So the timeline looks like this. First cold vacuum energy, then exponential inflation. Then the energy converts to matter and heat. That's the bang you've heard about. Inflation came before it. The question becomes sharper now. What scale of expansion are we describing? Numbers can be deceiving. When scientists say the universe doubled 80 times during inflation, it sounds almost modest. It's not. Each doubling multiplies size by 2. 80 doublings mean multiplying by 2 to the 80th power. Write that number out and you get something with 24 digits. The universe expanded by a factor of 1 septillion, or even more, depending on how long inflation lasted. This happened in approximately 10 to the negative 35 seconds. A decimal point followed by 34 zeros and then a 1. Human minds aren't built to grasp this. Let's try a comparison. Imagine a virus particle so tiny you'd need an electron microscope to see it. Inflate it through 80 doublings, and it becomes bigger than the entire observable universe. That's the expansion scale we're examining. What makes this scientifically credible is that it solves real observed problems. One is called the flatness problem. Space can curve like a sphere's surface, curve like a saddle, or be perfectly flat. Measurements show our universe is extraordinarily flat. So flat that if you fired a laser beam across the observable cosmos, it would travel in an almost perfectly straight path for 93 billion light years. The old model couldn't explain this. Tiny deviations from flatness in the early universe should have grown enormous over billions of years. We should live in a universe that curves dramatically. We don't. Inflation solves this by stretching space so extensively that any initial curvature got smoothed away. It's like inflating a balloon. The surface becomes flatter and flatter as it expands. Another problem is the horizon problem. Light has only had 13.8 billion years to travel since our bang began. That means regions of space separated by more than that distance have never been in contact. Yet when we measure their properties, they're identical. Same temperature, same expansion rate, same physical laws. How did they coordinate? Inflation answers this. Those distant regions were once close together, in contact, able to reach the same state. Then inflation separated them faster than light could reconnect them. The coordination happened before inflation, and the uniformity we observe today is the preserved memory of that earlier contact. The proof supporting these 80 doublings keeps getting stronger. Satellite missions have mapped the cosmic microwave background with incredible detail. The pattern of variations matches inflation predictions to a precision that stunned researchers. Alternative theories that don't invoke inflation fail to reproduce what we see. Scientists calculate that inflation must have lasted long enough for at least 80 doublings, possibly thousands more. The exact number remains uncertain because we can only see the effects within our observable universe. Inflation might have stretched space far beyond what we can detect, creating regions forever hidden beyond our cosmic horizon. This means the universe you can see, every galaxy, every star cluster, every bit of light, represents just one microscopic patch of a vastly larger reality. And it all came from a cold, empty vacuum expanding faster than physics should allow. What powered this impossible expansion? For decades, popular science portrayed our bang as the moment when time, space, and matter sprang into being from nothingness. That picture is outdated. Modern cosmology tells a different story. Our bang was not a creation event, it was a transformation. Specifically, it was the moment when the energy driving cosmic inflation converted into matter and radiation, flooding the universe with heat and particles. Think of it as a phase transition similar to water becoming steam, except far more violent and fundamental. This understanding comes from matching theory to observation. The cosmic microwave background radiation shows what the universe looked like 380,000 years after our bang. It's a nearly uniform glow with tiny temperature variations, exactly what you'd expect if the universe was once much hotter and denser, then expanded and cooled. But here's the critical insight. If we trace that expansion backward through time using Einstein's equations, we don't reach a real origin. We reach a barrier, a point where physics breaks down because temperatures and densities become too extreme for current theories to describe accurately. Scientists call this breakdown a singularity, but it's more honest to call it the edge of our knowledge. Inflation changes this picture completely. Instead of time starting at the singularity, time existed beforehand. During the inflationary phase, the universe was cold and empty, filled only with vacuum energy. Clocks ticked, space expanded, cause and effect operated normally. Then inflation stopped, and that's when our bang happened. The energy that had been locked in the vacuum state during inflation needed to go somewhere. Physical laws require energy conservation, so as inflation halted, the vacuum energy decayed. It transformed into elementary particles, quarks, electrons, photons, neutrinos. These particles carried enormous kinetic energy, making them move at nearly light speed. Their collisions created heat, vast heat. Within the first second after this transition, the universe reached temperatures of 10 billion degrees. Hot enough to prevent atoms from forming. Hot enough that only the most fundamental particles could exist. This seething plasma of matter and energy is what we call the early bang universe. But that heat wasn't present during inflation. Inflation was cold. The distinction is crucial. Our bang wasn't the beginning. It was the warming up that came after. Scientists have traced this transition using both theoretical calculations and experimental data. Particle accelerators like the Large Hadron Collider recreate early universe conditions by smashing protons together at enormous energies. These experiments confirm how matter behaves at extreme temperatures and validate the equations cosmologists use to model our bang. The timeline now looks clear. First, a cold quantum vacuum. Then inflation stretches it exponentially. Then the inflationary energy transforms into heat and particles. That transformation is the bang. After that comes the story you already know: cooling, atom formation, star birth, galaxy assembly. So when did time actually start? We're not certain yet. Possibly during inflation, possibly before. The honest answer is that we've pushed the boundary of the unknown backward, but we haven't eliminated it. And the evidence for all this gets even stronger. There's a smoking gun in the data proving the universe existed before the traditional bang. It's hidden in measurements of the cosmic microwave background, and it's called super-horizon fluctuations. Here's what that means. The cosmic horizon is the maximum distance light could have travelled since our bang began. It sets a limit on how far information can spread through the universe. Regions beyond this horizon have never been in contact with each other. They're causally disconnected. The standard bang model predicts that temperature variations in the cosmic microwave background should only exist on scales smaller than this horizon. Anything larger than the horizon represents regions that never interacted, so they shouldn't show coordinated patterns. But that's not what we see. The data reveals variations on scales larger than the cosmic horizon, much larger. These super-horizon features appear in multiple independent measurements taken by the WMAP satellite, the Planck satellite, and ground-based telescopes. The evidence is undeniable. How do you get coordinated patterns across regions that have never communicated? There's only one explanation. Those regions were in contact before our bang. During inflation, when the universe was tiny and cold, quantum changes occurred across all space. These changes became the seeds of structure. Then inflation stretched those changes to enormous sizes, far larger than the cosmic horizon. When our bang happened and hot matter filled the universe, these inflated quantum patterns were already imprinted on space. They showed up as temperature variations in the primordial plasma. We see those variations today as hot and cold zones in the cosmic microwave background. The math is exact. Inflation predicts a specific pattern of correlations between temperature and polarization in the cosmic microwave background. It predicts how the size of variations should change with scale. It predicts the spectrum of these variations should be nearly, but not perfectly, uniform across different sizes. Observations match these predictions with extraordinary precision. In 2003, the WMAP team published the first high-precision measurements showing the predicted correlation pattern, including features on super-horizon scales. The non-inflationary bang model predicted something entirely different. The data ruled out the old model and confirmed inflation. 20 years later, with even better instruments, the agreement has only improved. The Planck satellite mapped these variations with such exactness that scientists can now test inflation's predictions to fractions of a percent. Every test passes. The super-horizon correlations are exactly where they should be. This is one of the strongest pieces of proof in all cosmology. The patterns we see in the sky could not exist if our bang was the origin. They require a prior phase, inflation, where the universe was smaller, colder, and governed by different physics. Think about what this means. We've moved beyond philosophical speculation about before the bang. We have observational proof. The light from the ancient universe carries information about conditions that existed before the traditional bang happened. We can measure properties of that pre-bang state. We can test theories about it. The universe keeps secrets, but it also leaves clues. The cosmic microwave background is the oldest light in the universe, released 380,000 years after our bang. It's been travelling through space for over 13 billion years. When we capture this ancient radiation with telescopes, we're seeing a snapshot of the cosmos when it was young, hot, and simple. But hidden within that snapshot is information from even earlier, from the inflationary period before, our bang. Here's how that works. During inflation, the vacuum energy dominating the universe had quantum properties. Like everything in quantum mechanics, it experienced random changes. These weren't just microscopic ripples. Inflation amplified them, stretching microscopic quantum jitters into variations spanning millions of light years. When inflation ended and the bang transition occurred, those variations became imprinted on the distribution of matter and energy. Regions with slightly more density would eventually form galaxy clusters. Regions with slightly less density would become cosmic voids. The structure of the entire universe traces back to quantum randomness during inflation. The cosmic microwave background captures this information because the photons, released 380,000 years after our bang traveled through space, that already had these density variations. Hot zones in the radiation come from regions that were slightly denser. Cool zones come from regions that were less dense. The pattern we see today is a fossilized map of conditions created during inflation. Scientists have measured this map with incredible detail. The temperature varies by only a few parts per 100,000. The universe was remarkably uniform even then. But within that uniformity lies structure. Specific sizes of hot and cold regions appear more frequently than others, creating what cosmologists call the power spectrum. Inflation makes exact predictions about what this power spectrum should look like. The distribution of fluctuation sizes should follow a nearly scale-invariant pattern, meaning fluctuations of different sizes have almost the same amplitude. Observations confirm this prediction. The match is so close that it's become one of the fundamental pillars of modern cosmology. But the cosmic microwave background reveals more than just density variations. It also carries information about polarization, the orientation of the electromagnetic waves. This polarization gets affected by gravitational waves, and inflation should produce gravitational waves as a byproduct of its exponential expansion. Detecting these primordial gravitational waves remains one of cosmology's biggest goals. If found, they would provide direct proof of inflation's energy scale and offer a window into physics at temperatures far beyond what particle accelerators can reach. Multiple experiments are searching for this signal right now. Even without detecting gravitational waves yet, the temperature and polarization data we already have constrains inflation theories. Some models predict large gravitational wave signals. Those models are now ruled out. Other models predict specific patterns in how variations behave on different scales. Observations test those predictions and eliminate models that don't match. The cosmic microwave background has become a laboratory for studying the pre-bang universe. Every improvement in measurement technology brings new insights. The data keeps improving, and the picture of inflation keeps getting clearer. What it reveals is a universe that existed in a state completely different from anything we experience today. We assume time flows in one direction, from past to future. We remember yesterday, but not tomorrow. Causes come before effects. The sequence of moments feels fundamental to reality. But what if time itself only started during inflation, or even later? This isn't wild guessing. It comes from taking Einstein's general relativity seriously. Einstein showed that time and space are linked to space-time, a four-dimensional fabric that can bend, stretch, and warp. Gravity isn't a force acting through space and time. Gravity is the curvature of space-time itself. This means time is physical. It's part of the universe, not something external that the universe exists within. And if time is physical, then asking what happened before the universe existed might be like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Stephen Hawking explored this idea using quantum mechanics. Working with James Hartle, he proposed the no-boundary hypothesis. The math describes the universe's origin using something called imaginary time, a concept from quantum theory where time behaves like a spatial dimension. In this framework, the universe doesn't have a beginning point. Instead, it smoothly transitions from a timeless quantum state into the classical space-time we experience. Think of Earth's surface. If you travel south, you eventually reach the South Pole. You can't go farther south because there is no farther south. you've reached the limit. The no-boundary proposal suggests something similar for time. Trace cosmic history backward, and you eventually reach a boundary where time itself curves back on itself. There's no before because time doesn't extend in that direction. This creates a strange picture. The universe is finite in time but has no beginning moment. It's self-contained. No creator needed, no violation of causality, no infinite past to explain. Other physicists disagree. Julian Barber argues that time is an illusion emerging from the changing patterns of matter. According to his view, only the present moment exists. The past is a memory stored in the current arrangement of particles. The future hasn't happened yet, so it doesn't exist. If time is illusory, then asking about before our bang becomes meaningless in a different way. The confusing part is that both perspectives might be partially correct. At everyday scales, time behaves as we expect. Clocks tick, causes produce effects. The arrow of time points clearly forward. But at the quantum scale governing the universe's origin, time becomes fuzzy and uncertain, just like position and momentum. During inflation, if it occurred, time likely existed in a normal sense. The vacuum energy state could last for a duration. Space could expand over time. But before inflation, that's where our understanding fails. The mathematical singularity at the start of time might be telling us that general relativity breaks down and a quantum theory of gravity is needed. Nobody has successfully combined quantum mechanics and general relativity into a complete theory yet. Without that theory, questions about the ultimate origin remain open. We can trace cosmic history back to the Planck time, 10 to the negative 43 seconds after our bang. Earlier than that, our physics doesn't work. What does before even mean in that regime? Language fails us when discussing the origin of time. Every word we use assumes time already exists. Before implies an earlier moment. Cause implies something happening first. Beginning suggests a transition from not existing to existing. But if time itself emerged with the universe, these concepts collapse into paradox. Cosmologists wrestle with this constantly. They need to communicate ideas that transcend normal experience using words built for normal experience. The result can sound contradictory or confusing, but the confusion comes from the limits of language, not necessarily the limits of reality. One approach is to abandon the idea of before entirely. Georges Lemaitre, the Belgian priest and physicist who first proposed cosmic expansion, suggested the universe started in a day without yesterday. St. Augustine made a similar argument 1,600 years earlier, claiming time was created along with the universe, so asking what came before is nonsensical. Modern physics provides a framework for this. General relativity describes space-time as a manifold, a mathematical structure with definite boundaries. Time could have a boundary at our bang, just as Earth's surface has a boundary at the poles. Asking what's before the boundary is like asking, what colour is Tuesday? The question contains a category error. But here's where it gets interesting. Quantum mechanics might allow an escape from this conclusion. In quantum theory, particles can tunnel through barriers they shouldn't be able to cross. Electrons tunnel through insulators. Alpha particles tunnel out of atomic nuclei. It's a thoroughly validated phenomenon. Some physicists propose the universe itself tunneled into existence from a quantum vacuum state. Alexander Vilenkin developed this idea in detail. He describes a scenario where a universe with zero size has some small quantum probability of tunneling into a state with non-zero size. Once it makes that transition, inflation takes over and expands it to cosmic proportions. In this picture, there is no before. in the usual sense, but there is a prior quantum state, the vacuum from which the universe tunneled. Time starts when the universe achieves classical space-time properties, but the quantum state exists outside of time as we understand it. David Bohm's pilot wave interpretation of quantum mechanics offers another perspective. In Bohm's framework, particles have definite positions at all times, guided by a quantum potential. When applied to cosmology through the Wheeler-DeWitt equation, this suggests the universe could have definite properties even at the moment of origin. The quantum potential acts like an effective cosmological constant driving the initial expansion. These ideas remain theoretical, but they point toward a resolution. Maybe before our bang doesn't mean earlier in time. Maybe it means prior in some other sense, causally prior, logically prior, or quantum mechanically prior. The state from which the universe emerged wouldn't exist at a moment before time started. It would exist outside the framework of time altogether. This challenges our intuition deeply. We're used to thinking of existence as happening in time, but quantum states don't necessarily exist in time. They exist in configuration space, an abstract mathematical realm describing all possible states a system could occupy. The universe's emergence could be a transition from one configuration to another, with time itself being a feature that emerges during the transition. Philosophers have argued about these questions for millennia. Physics now provides us tools to make those arguments exact, testable, and grounded in observation. We may never have a complete answer, but we're asking better questions. And some theories go even further. What if our universe wasn't born from nothingness, but from a collision? What if everything we see came from two massive structures smashing together in a higher dimension? This is the ekpyrotic model, and it's built on serious math. The theory emerges from string theory, a framework that describes particles as tiny vibrating strings rather than point-like objects. String theory requires extra dimensions beyond the three of space and one of time we experience. These dimensions could be curled up small, or they could be large but hidden from our direct perception. In some versions of string theory, our universe exists on a three-dimensional membrane, or brain, floating in higher dimensional space. Think of a sheet existing in a three-dimensional room. We're trapped on the sheet, unable to move off it, while the room contains other dimensions we can't access. The ekpyrotic model, proposed in 2001 by physicists including Paul Steinhardt and Neil Turok, suggests there are two such brains parallel to each other. An attractive force pulls them together over vast spans of time. They approach slowly, then they collide. The collision releases enormous energy. From our perspective, trapped on one brain, this would look like our bang. Matter and radiation flood our three-dimensional space. The universe heats up, expands, cools, and evolves into the cosmos we observe today. But it wasn't a beginning, it was a crash. This theory solves several problems that inflation struggles with. It explains why the universe is flat and uniform without requiring exponentially rapid expansion. The slow approach of the brains smooths out any irregularities before impact. It explains the pattern of variations in the cosmic microwave background as vibrations created by the collision. And it avoids the multiverse problem plaguing inflationary models. Inflation, if it lasts long enough, produces an infinite number of pocket universes with random properties. This makes the theory hard to test, because any observation can be explained as, we just happen to live in this pocket. The ekpyrotic model doesn't have this issue. One collision creates one universe with predictable properties. But the ekpyrotic scenario faces challenges. Nobody fully understands what happens during a brain collision. String theory isn't developed enough yet to precisely calculate the outcome. Some critics argue the collision might destroy the smoothness the model depends on. Others point out that getting the correct spectrum of density variations requires fine-tuning the collision parameters. Despite these difficulties, the ekpyrotic model remains scientifically viable. It makes testable predictions. For instance, it predicts gravitational waves from the collision would be too weak to detect in the cosmic microwave background. Inflation predicts they might be detectable. Future observations could distinguish between these scenarios. The ekpyrotic model also connects to something deeper, the idea that our bang wasn't unique. If brains can collide once, they can collide multiple times. The collision could bounce the brains apart. They'd separate, drift in the higher dimension, then get pulled back together by the attractive force. Another collision, another bang. This leads to a cyclic cosmology where the universe goes through endless cycles of collision and separation. Each cycle creates a cosmos. Each cycle ends when the brains separate. Then the process repeats. From our perspective, it would look like the universe expands, then contracts, then bounces into a new expansion. Except the bounce happens through a collision in a higher dimension, not a simple reversal of our three-dimensional space. The implications are staggering. The singularity at the start of our bang has haunted physics for decades. A point of infinite density, infinite temperature, infinite curvature. A place where equations break down and give nonsensical answers. Most physicists don't believe the singularity is real. They see it as a sign that general relativity fails under extreme conditions. The Big Bounce theory offers a solution. Instead of the universe starting at a singularity, it transitions smoothly from a contracting phase into our current expanding phase. The bounce happens at a finite, though extremely high density. No infinities, no breakdown of physics. This isn't just wishful thinking, it's grounded in loop quantum gravity, an approach to combining quantum mechanics and general relativity. In loop quantum gravity, space itself has a discrete structure at the tiniest scales, like pixels on a screen. When you try to compress matter and energy into an infinitely small point, the quantum properties of space prevent it. There's a minimum volume. A bounce becomes inevitable. Calculations using loop quantum gravity show that a collapsing universe would reach a maximum density, then rebound into expansion. The math is complex, but the conclusion is clear. Quantum effects create a repulsive force at extreme densities that overwhelms gravity. Think of it like compressing a spring. Push too hard and it pushes back. Recent work published in 2020 by Robert Brandenberger and Ziwei Wang explored how a bounce could produce the observed features of our universe. They found that if the pre-bounce universe underwent a phase of slow contraction, similar to inflation but in reverse, it could create the same pattern of density variations we see in the cosmic microwave background. This means the universe before the bounce might have looked like ours in reverse. Galaxies merging instead of separating. Light shifting toward blue instead of red. Time running backward from our perspective, though forward from the perspective of observers living in that era. When the bounce occurred, information from the pre-bounce universe could have survived the transition. The variations in matter and energy distributions would carry through, seeding structure in the post-bounce cosmos. This creates a radical picture. Our bang wasn't the start, it was the midpoint of a much longer story. Before our expansion came a contraction. Before that, possibly another expansion. The universe might be far older than 13.8 billion years. It might have no age at all, stretching infinitely into the past through endless cycles. The Big Bounce avoids many philosophical problems plaguing creation from nothing scenarios. It doesn't require explaining why the universe exists rather than nothing. It doesn't require a moment when time starts. It simply requires quantum gravity to behave the way loop quantum gravity predicts. Testing this theory is challenging. The bounce itself happened under conditions we can't reproduce in laboratories. But the theory makes predictions about the cosmic microwave background and the spectrum of gravitational waves that might be detectable. Several experiments are searching for these signatures. If the Big Bounce is correct, then the question shifts. We don't need to explain the universe's creation. We need to explain its structure and its cycles. Which brings us to the most ambitious idea yet. Imagine a cosmos that never started and never ends. A universe caught in an eternal rhythm of expansion, contraction, bounce, and expansion again. Each cycle lasting trillions of years, each cycle creating the conditions for stars, planets, and possibly life. This is cyclic cosmology. The idea isn't new. Ancient Stoic philosophers proposed an eternal cycle of cosmic creation and destruction they called ekpyrosis. Hindu cosmology describes similar cycles over vast timescales. But modern physics puts these concepts on firm mathematical ground. In the cyclic model developed by Paul Steinhardt and Neil Turok, dark energy plays a crucial role. Remember, dark energy is the mysterious component causing our universe's expansion to accelerate. In their model, dark energy eventually pushes galaxies so far apart that the universe becomes essentially empty. Matter gets diluted to negligible density. Stars burn out. Black holes evaporate through Hawking radiation over incomprehensible time spans. But the dark energy doesn't disappear. It continues to exist. And in the ekpyrotic cyclic model, it acts as a bridge to the next cycle. The same attractive force between brains that caused our bang collision continues to operate. Over trillions of years, it pulls the brains together again. Another collision occurs. Another bang erupts. A new universe starts. Crucially, each cycle doesn't produce identical conditions. The universe grows larger with each iteration. The scale factor, a measure of cosmic size, increases exponentially from cycle to cycle. Entropy builds up, but it gets diluted by the expansion. The second law of thermodynamics isn't violated because the universe keeps becoming bigger, giving entropy more room to spread. This solves the entropy problem that killed earlier cyclic models. In the 1930s, physicist Richard Tolman showed that a naively cyclic universe would accumulate entropy until it couldn't bounce anymore. The Steinhardt-Turok model avoids this by incorporating dark energy and allowing the universe to expand net over many cycles. Another cyclic proposal comes from Roger Penrose, the Nobel laureate mathematician. His conformal cyclic cosmology suggests the universe expands forever until all matter decays into radiation. At that point, nothing remains with rest mass. Everything moves at light speed. When nothing has mass, the concepts of time and distance become meaningless. Penrose argues this massless state can be mathematically mapped onto a new bang. The infinite future of one universe becomes the bang of the next. It's conformal because the geometry is preserved under this transformation. Even though scales change, time becomes circular, or perhaps spiral. These models remain speculative, but they're testable. They predict specific patterns in the cosmic microwave background. Some versions predict we might see circular patterns from collisions in the previous cycle, like ripples on a pond imprinted in the radiation. Searches have been conducted. So far, no definitive signals found. But the search continues. Cyclic cosmology offers philosophical appeal. It removes the awkward question of why the universe exists. It always has existed and always will, changing form but never truly starting or ending. Existence becomes fundamental, while specific arrangements like our current expanding universe become temporary phases. But it also raises new questions. If cycles repeat forever, have there been infinite cycles? Does the universe have a memory of earlier cycles? Are the physical laws the same in each cycle, or do they evolve? We may be on the verge of answering some of these questions. Here's a possibility that sounds like fiction but emerges from serious theoretical work. Each cycle of the universe might operate under different physical laws. The constants governing particle masses, force strengths, and cosmic behavior could shift from one cycle to the next. Why would this happen? In many theoretical frameworks, the values of physical constants aren't set by fundamental principles. They're environmental, determined by how quantum fields settle into their lowest energy states. It's like water freezing. The exact pattern of ice crystals depends on random changes during the freezing process. During a bounce or brain collision, the extreme energies could reset these fields. As the new universe expands and cools, the fields would settle into new arrangements, different constants, different physics, a cosmos that looks and behaves differently from ours. This has profound implications. In most cycles, the constants might not allow complex structures to form. Galaxies wouldn't gather, stars wouldn't ignite, chemistry might not exist. Those universes would be sterile, simple, and short-lived. But occasionally, by random chance, the constants would align just right. Atoms could form, complexity could emerge, life might evolve. We find ourselves in one of those rare successful cycles because we couldn't exist in any other kind. This is a version of the anthropic principle, the observation that the universe must be compatible with the conscious life that observes it. In a cyclic multiverse where each cycle has different physics, the anthropic principle explains our particular set of constants without requiring fine-tuning. Some physicists find this explanation unsatisfying. It replaces the mystery of why our constants have life-permitting values with the assumption that all possible values occur somewhere in the cyclic sequence. You haven't really explained anything, you've just moved the mystery one level deeper. Others embrace it. If the cyclic model is correct and constants vary between cycles, then we can make statistical predictions. We should find ourselves in a typical, life-permitting cycle, not a maximally life-permitting one. Our universe should be close to the boundary where complex structures barely form. Too far from the boundary would be statistically unlikely. Some evidence tentatively supports this. The cosmological constant in our universe sits uncomfortably close to the maximum value that would allow galaxies to form. Much larger and cosmic expansion would have accelerated so rapidly that matter could never clump together. Much smaller, and we'd need to explain why it's not exactly zero. We seem to be near a boundary, which cyclic anthropic reasoning predicts. Testing whether constants varied in previous cycles is nearly impossible. The bounce erases most information. But some frameworks suggest subtle imprints might survive. Topological defects, certain kinds of knots in space-time, could potentially persist through a bounce and leave detectable traces. More realistically, we can test whether the framework allowing variable constants makes sense. String theory, for instance, predicts a vast landscape of possible vacuum states, each with different effective physical laws. Exploring which of these states are accessible and how transitions between them might occur is active research. The big picture emerging from cyclic cosmology with variable physics is humbling and grand simultaneously. Our universe isn't special. It's one outcome of an eternal process that creates cosmos after cosmos. Most of them failures, some of them interesting, a few of them giving rise to observers who can ask these questions. We're left with a vision of reality far stranger than the simple something from nothing narrative. There might be no ultimate beginning, no final end, no single set of physical laws, just an infinite churning of possibilities with brief windows where complexity flourishes before collapsing back into simplicity, then re-emerging in a new form. The universe in this view is not a creation, but an eternal transformation. General relativity and quantum mechanics are the two pillars of modern physics. General relativity describes gravity, black holes, and cosmic expansion. Quantum mechanics governs atoms, particles, and the microscopic world. Both frameworks work brilliantly in their domains, but they contradict each other at extreme scales. Loop quantum gravity attempts to resolve this conflict by applying quantum principles to space and time themselves. Instead of treating space as a smooth continuum, loop quantum gravity describes it as a network of discrete loops, microscopic quantum units connected like chainmail. At normal scales, this discrete structure averages out and space appears smooth, just like a television screen appears continuous from a distance, but is actually made of pixels. The key insight arrives when you apply these ideas to the bang singularity. In classical general relativity, matter collapses to infinite density, but loop quantum gravity says space has a minimum volume. You can't compress something smaller than the fundamental quantum unit of space, which exists at the Planck scale, about 10 to the negative 35 meters. When a collapsing universe reaches this density, quantum repulsion activates. The math shows that gravity effectively reverses, becoming repulsive instead of attractive. The collapse stops and reverses into an expansion. The singularity gets replaced by a bounce, a smooth quantum bridge connecting contraction to expansion. This isn't speculation. Scientists have performed detailed calculations using loop quantum gravity equations. They've simulated how a universe evolves through the bounce. The results show that cosmological perturbations, the tiny variations seeding galaxies, can propagate through the bounce without being destroyed. Information survives the transition. Abhay Ashtekar and his collaborators at Penn State have led much of this research. They've shown that a pre-bounce universe undergoing slow contraction would create a nearly scale-invariant spectrum of perturbations matching what we see in the cosmic microwave background. The bounce doesn't erase this structure, it preserves it. This creates a testable prediction. Loop quantum gravity bounces should produce specific signatures in gravitational waves. The spectrum should differ slightly from what inflation predicts. As gravitational wave detectors become more sensitive, they might distinguish between these scenarios. There's also a philosophical shift here. Loop quantum gravity doesn't require anything beyond known physics. It doesn't invoke extra dimensions, colliding brains, or exotic forms of matter. It simply takes quantum mechanics seriously at all scales, including space-time itself. The singularity that terrified physicists for decades disappears. It was never real, just an artifact of using classical equations where they don't apply. Once you account for quantum effects, the universe has no beginning or end in the traditional sense. It's a continuous process, with phases of expansion and contraction connected by quantum bridges. This resolves the paradox of creation. You don't need to explain how something came from nothing because there was never nothing. There was always a quantum space-time structure, eternally transforming between different states. But what triggered our particular phase? One of the strangest ideas in cosmology sounds like circular logic but might be real. The universe could have created the conditions that allowed it to exist. It bootstrapped itself into reality through a self-consistent loop. Here's how this works. In quantum mechanics, the future can influence the past through what's called retrocausality. When you measure a particle's state, you don't just observe what it is, you retroactively determine what it was. The act of measurement reaches backward through time and selects which possibility becomes real from a cloud of quantum probabilities. John Wheeler, one of the great physicists of the 20th century, proposed the universe might work the same way. He called it the participatory anthropic principle. The existence of observers who can measure and understand the universe contributes to bringing that universe into existence. The cosmos creates observers who look back at its origin, and through that observation help define what the origin was. This sounds mystical, but it emerges naturally from certain interpretations of quantum mechanics. The universe's wave function describes all possible arrangements it could have. When conscious observers emerge and begin making measurements, they collapse parts of this wave function, selecting which history actually occurred. In this view, our bang wasn't just a random event. It was the only event consistent with a universe that would eventually produce observers. Other possible initial conditions might have led to sterile universes with no complexity. Those branches of the wave function never got actualized because no observers existed to collapse them into reality. This creates a causal loop. The universe exists in a form that allows observers. The observer's existence retroactively selects the initial conditions that led to them. The initial conditions cause the observers. The loop is self-consistent. Physicist James Hartle has explored these ideas mathematically. His work with Stephen Hawking on the no-boundary proposal incorporates this self-selection principle. The universe doesn't have a single fixed past. It has a superposition of possible pasts, and the act of existing in the present helps determine which past becomes real. Other frameworks reach similar conclusions through different routes. In Lee Smolins' cosmological natural selection, universes that produce black holes create baby universes through quantum tunneling. Each baby universe has slightly different physical constants. Over many generations, this process selects for universes optimized to produce black holes, which also happen to be good at producing stars, planets, and complexity. We exist in such a universe not by chance, but because only this type of universe can persist through the selection process. The universe bootstraps its own existence through an evolutionary mechanism spanning across cosmic generations. These ideas remain controversial and difficult to test, but they point toward a resolution of the deepest mystery. Why is there something rather than nothing? The answer might be that nothing is unstable in a quantum framework. Any fluctuation that creates something which can sustain itself will persist. Others collapse. We observe a self-sustaining arrangement because non-sustaining ones don't produce observers. The universe exists because it can exist. The conditions making it possible are the conditions it selects for through its own evolution. Reality is a strange loop that creates itself, and the mathematics describing this gets even stranger. We experience 3 dimensions of space: left-right, forward-backward, up-down. Add time and you get 4 dimensions. String theory says there are at least 7 more hidden dimensions, giving a total of 11. Why haven't we noticed them? The theory proposes they're compactified, curled up so tiny that we can't perceive them. Imagine an ant walking on a telephone wire. From far away, the wire looks one-dimensional. The ant can only move forward or backward. But up close, the wire has thickness. The ant could walk around its circumference, exploring a second dimension we initially missed. The extra dimensions in string theory work similarly. They exist at every point in our 3-dimensional space, but they're rolled up at scales far smaller than atoms. Particles can vibrate through these hidden dimensions, and different vibration patterns appear to us as different particle types. An electron is one vibration mode, a quark is another. Photons, neutrinos, everything emerges from strings vibrating through this higher dimensional space. This framework has profound implications for cosmology. Our universe might be a three-dimensional surface embedded in this higher dimensional space. Everything we see, stars, galaxies, light, is trapped on this surface. But gravity is different. Gravitational effects can leak into the extra dimensions, which might explain why gravity is so much weaker than the other fundamental forces. The ekpyrotic model we discussed earlier exploits this. If parallel three-dimensional branes exist in the higher dimensional bulk, and if they can move through those extra dimensions, then collisions become possible. Our bang would be the aftermath of such a collision, with the pre-collision state existing in this higher dimensional framework. String theory also suggests that different compactifications of the extra dimensions produce different physical laws. There might be 10 to the 500th or more distinct ways to curl up the extra dimensions, each creating a different vacuum state with different particle masses and force strengths. This vast landscape of possibilities connects to the idea of varying constants between cosmic cycles. Testing these ideas is extraordinarily difficult. The energies needed to probe the extra dimensions directly exceed anything achievable in particle accelerators by many orders of magnitude. But indirect evidence might exist. Gravitational waves propagating through the bulk could carry signatures of extra dimensions. Tiny deviations in how gravity behaves at small scales might reveal the geometry of hidden dimensions. Experiments at the Large Hadron Collider searched for signs of extra dimensions by looking for missing energy in particle collisions. If particles escaped into the bulk, energy would seem to disappear. So far, no definitive signals, but the search continues at higher energies and with greater precision. String theory remains incomplete and controversial. Some physicists embrace it as the best candidate for a theory of everything. Others criticize it for making few testable predictions and requiring fine-tuning to match observations. The debate continues, but the core insight persists. The universe we observe might be a shadow of a larger reality. The three dimensions of space we navigate might be an illusion, a projection of something far more complex existing in realms we can't directly access. This raises a question about the pre-bang state. If extra dimensions exist, what role do they play in the universe's origin? Inflation was supposed to be a one-time event, a brief phase of exponential expansion that set up our bang, then ended. But the mathematics suggests something far stranger. Once inflation starts, it might never completely stop. Here's why. Inflation is driven by a quantum field called the inflaton. When this field sits at a high energy value, space expands exponentially. As the field rolls down toward lower energy, inflation slows and eventually stops. The field's energy converts to matter and radiation. That's the bang we know. But quantum changes affect the inflaton field just like they affect everything else. In some regions of space, random changes push the field back up to higher energy before it can finish rolling down. Those regions keep inflating. Meanwhile, other regions successfully end inflation and produce hot bang conditions. This creates a fractal structure. Our observable universe is a pocket where inflation ended. But beyond our cosmic horizon, other regions are still inflating. And within those inflating regions, new pockets constantly form where inflation stops. Each pocket becomes a bang universe. Each one expands, cools, and potentially develops galaxies, stars, and life. The process never ends. Alan Guth and André Linde developed this eternal inflation framework in the 1980s. It's a natural consequence of combining inflation with quantum mechanics. The implications are staggering. There's not one universe. There's a vast, possibly infinite multiverse. Our bang is just one bubble in an endless foam of universes. Each bubble might have different properties. The quantum changes creating new pockets could also affect the values of physical constants, producing pocket universes with different physical laws. This solves some mysteries while creating others. It explains why our universe has life-permitting constants. There are infinite universes with all possible constants. We necessarily find ourselves in one compatible with our existence. But it also means the theory can't predict what we should see, because every possible observation occurs somewhere in the multiverse. Eternal inflation also has a past. The Border-Guth-Vilenkin theorem, proved in 2003, shows that any region of space expanding on average must have a boundary in the past. Inflation can't be eternal into the past. It must have started somehow, from some initial state. This brings us back to the origin question. What triggered inflation in the first place? The metastable false vacuum? A quantum change? A prior contracting phase? The theorem doesn't tell us what came beforehand, but it proves there was a beforehand. Some physicists find eternal inflation disturbing. It seems to make science impossible if every outcome exists somewhere. Others argue we can still make probabilistic predictions by counting which types of observers are most common across the multiverse. The debate is unresolved, but the math of eternal inflation is solid. Unless quantum mechanics or the inflaton field behaves very differently than we think, the multiverse seems unavoidable. What does this mean for the concept of nothingness? Stand back and look at the big picture. If eternal inflation is correct, reality is not a single universe with one bang. It's an infinite collection of disconnected regions, each with its own bang, expanding within an ever-inflating background. Think of it as quantum foam on a cosmic scale. The inflating space is the substance. The pocket universes are bubbles forming within it. Each bubble thinks it's the entire universe because the inflating background expands faster than light, forever hiding other bubbles beyond an unreachable horizon. This structure might be nested. Within each pocket universe, if conditions allow, new phases of inflation could start. Those would spawn their own sub-pockets. You'd get a hierarchy of nested realities, each level spawning the next, all embedded within the eternal inflation that never stops. Max Tegmark has classified different types of multiverses. Level 1 is simply distant regions of our own universe, beyond our observation horizon, but obeying the same physics. Level 2 is the eternal inflation multiverse we're discussing, different bubbles with potentially different physical constants. Level 3 involves the many worlds interpretation of quantum mechanics, where every quantum measurement splits reality into branches. Level 4 would be completely different mathematical structures obeying different logical rules. The Level 2 multiverse from eternal inflation is the most scientifically grounded. It emerges directly from combining well-tested physics, general relativity, quantum mechanics, and inflation. You don't need to assume anything exotic. The multiverse is a consequence, not an assumption, but it creates an observability problem. We can only see inside our bubble. The inflating background between bubbles expands so rapidly that light from other bubbles can never reach us. They're not just far away, they're causally disconnected. No information can travel between bubbles. Each pocket universe is fundamentally isolated. This seems to put other bubbles beyond science's reach. If we can't observe them, test predictions about them, or interact with them in any way, are they really scientific entities, or have we crossed into metaphysics? Some argue the multiverse remains scientific because it's a prediction of testable theories. We don't test the multiverse directly, we test inflation. If inflation is correct, eternal inflation follows naturally. Rejecting the multiverse means rejecting the logical consequences of confirmed physics. Others remain skeptical. They argue that good scientific theory should make definite predictions about what we see. The multiverse allows anything, which means it predicts nothing. It's a failure of our theories, not a feature of reality. The debate continues, but observationally we're stuck in our bubble. We can study its properties. We can map the cosmic microwave background. We can measure the expansion rate and the dark energy density. All of this tells us about our pocket universe. Whether infinite other pockets exist remains unknown, but the math strongly suggests they do. And if they do, then the question of what existed before our bang gets even stranger. Our bang was not the start of inflation. It was the end of inflation in our local region. Other regions never stopped inflating. Still others ended inflation earlier or later. There's no universal before the bang. Each pocket has its own timeline, its own origin, its own history. The multiverse as a whole might be timeless, with pockets starting and ending at all moments, embedded in an eternal background. This is the picture modern cosmology paints. Not a simple creation story, a complex layered reality where our universe is one small piece. For decades, popular science treated the bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved. But physicists never believed it. A singularity signals the breakdown of your theory, not a description of reality. When equations give infinite answers, they're telling you the mathematical framework no longer applies. You've pushed the model beyond its domain of validity. General relativity predicts singularities. Black holes have them at their centers. Our bang has one at its start. But general relativity is a classical theory. It doesn't include quantum mechanics. At small scales and high energies, quantum effects become crucial. Ignoring them guarantees your prediction will fail. Think of it like predicting the behavior of water. Classical fluid mechanics works great for describing rivers, waves, and pipes. But at molecular scales where individual water molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're the wrong tool. General relativity is the wrong tool at Planck scales. The Planck length is 10 to the negative 35 meters. The Planck time is 10 to the negative 43 seconds. The Planck energy is about 10 to the 19 Geiger electron volts, roughly the energy of a flying mosquito compressed into a single particle. These are the scales where quantum gravity becomes essential. At these scales, space and time stop behaving classically. They fluctuate. They become uncertain. The very concepts of distance and duration lose their usual meanings. A singularity, which requires compressing something into exactly zero volume, becomes impossible. Quantum mechanics won't allow it. Stephen Hawking and Roger Penrose proved theorems showing that general relativity predicts singularities under very general conditions. Their work was brilliant and crucial, but it also highlighted exactly where general relativity fails. The singularity theorems tell us where we need a better theory. Loop quantum gravity replaces the singularity with a bounce. String theory might replace it with a minimum size determined by string length scales. Other quantum gravity proposals have their own solutions. The details differ, but the conclusion is the same. The singularity isn't real. This means our bang wasn't a moment when the universe sprang from nothing into something. It was a transition from one quantum state to another. The pre-transition state might have been a contracting universe, an inflating vacuum, a higher dimensional brain arrangement, or something else entirely. But it was something, not nothing. The mathematical fiction of the singularity misled generations of physicists and the public. It made the universe's origin seem more mysterious than it is. Yes, we don't fully understand quantum gravity. Yes, the precise details of the transition remain unclear. But we know the universe didn't start at an infinitely dense point because infinite density is unphysical. This shifts the question. We're not trying to explain how something came from absolute nothing. We're trying to explain what the pre-bang quantum state was and why it transitioned into our current expanding universe. That's still a profound question, but it's a tractable one. Quantum mechanics and general relativity are both experimentally validated to incredible precision. Quantum mechanics predicts the behavior of atoms, lasers, and computer chips with perfect accuracy. General relativity predicts the orbits of planets, the bending of light around galaxies, and the detection of gravitational waves. Both theories work flawlessly in their domains, but they contradict each other when you try to combine them. This isn't a minor technical issue, it's a fundamental clash of principles. In quantum mechanics, you can measure a particle's energy with arbitrary precision if you're willing to wait long enough. Time is a background parameter that flows uniformly. In general relativity, time is part of space-time, which curves and warps. Time runs at different rates depending on gravity and motion. There's no universal clock. In quantum mechanics, particles exist in superpositions. An electron can be in multiple locations at once until you measure it. In general relativity, space-time has a definite geometry. You can't have space-time in a superposition of different curvatures. Or can you? These contradictions become critical at Planck scales, where both quantum effects and gravitational effects are strong. You need a theory of quantum gravity, a theory that incorporates both sets of principles consistently. Nobody has one yet that's complete, tested, and universally accepted. String theory offers one approach. It replaces point particles with vibrating strings. This smooths out the singularities plaguing quantum gravity calculations. The math is elegant, and the theory potentially describes all forces and particles within one framework. But it requires extra dimensions, has many possible solutions, and makes few testable predictions at accessible energies. Loop quantum gravity takes a different route. It quantizes space-time directly, treating it as a network of discrete loops. This avoids singularities and explains how space emerges from quantum building blocks, but it struggles to incorporate matter and forces beyond gravity. Connecting it to particle physics remains challenging. Other approaches exist. Causal dynamical triangulations build space-time from simple geometric pieces and evolve it through quantum rules. Asymptotic safety suggests gravity might remain well behaved at high energies through a special mathematical property. Emergent gravity frameworks propose that space-time isn't fundamental, but emerges from more basic quantum information. Each approach has strengths and weaknesses. Each makes different predictions about Planck-scale physics. And frustratingly, directly testing these predictions is nearly impossible with current technology. The energies are too high. The scales are too small. But cosmology provides an indirect testing ground. The early universe naturally probed Planck-scale physics. If we can decode the messages written in the cosmic microwave background, in the spectrum of gravitational waves, in the distribution of large-scale structure, we might distinguish between competing quantum gravity theories. This is why understanding what happened before our bang matters scientifically. It's not just philosophical curiosity, it's a window into the most fundamental laws of physics. The universe's origin is the one natural laboratory where quantum gravity was fully operational, leaving fingerprints we can potentially read. The battle between quantum mechanics and general relativity will be resolved. When it is, we'll have a complete picture of how space-time and matter operate at all scales. And with it, we'll understand what nothingness really means in the deepest sense. One equation might hold the key. In 1967, John Wheeler and Bryce DeWitt derived an equation attempting to describe the quantum state of the entire universe. It's deceptively simple looking, but it contains profound implications for cosmology and the question of origin. The Wheeler-DeWitt equation treats the universe's geometry and matter content as quantum variables. Just as an electron has a wave function describing its possible positions, the universe has a wave function describing its possible configurations. The equation tells you how this wave function evolves, not in time, but in terms of relationships between different geometries. Here's the strange part. The equation doesn't contain time. There's no variable representing when things happen. Instead, it describes correlations between different aspects of the universe's state. It's sometimes called the equation with no time, and it raises deep questions about whether time is fundamental or emergent. When applied to cosmology, the Wheeler-DeWitt equation allows solutions where a universe tunnels into existence from a state with zero size. This isn't a metaphor, it's a quantum mechanical process, analogous to how particles tunnel through barriers. The universe starts in an arrangement that classically couldn't expand, then quantum tunneling allows it to jump to an arrangement that can. Alexander Vilenkin developed this universe from nothing scenario using the Wheeler-DeWitt equation. In his framework, the nothing is a quantum vacuum state with no classical spacetime. The universe tunnels from this state into a small closed space that immediately begins inflating. From our perspective inside the universe, it looks like time starts at the moment of tunneling, but calling it nothing is misleading. The quantum vacuum state exists. It has properties. It's described by mathematical laws. It's not absolute philosophical nothingness. It's the quantum mechanical ground state before classical time emerges. Other solutions to the Wheeler-DeWitt equation exist. The Hartle-Hawking no-boundary proposal uses imaginary time to smooth out the singularity. Bohm's pilot wave interpretation suggests the quantum potential in the equation acts like an effective cosmological constant. Each approach gives different insights into what the pre-classical state might be. Chinese physicists Dongshan He, Dongfang Gao, and Qing-Yu Kai published work in 2014 exploring spontaneous creation solutions. They showed that under certain conditions, a Planck-sized vacuum bubble has a non-zero quantum probability of expanding rather than collapsing. Once expansion starts, inflation takes over and creates a universe. The probability is tiny, but in a timeless quantum realm where all possibilities exist in superposition, tiny probabilities become actual outcomes given enough trials. And in an eternal quantum foam of fluctuating vacuum states, every possibility eventually happens. This provides a mechanism for the universe's origin that doesn't require an external cause. The quantum vacuum is inherently unstable. Virtual changes constantly occur. Most collapse immediately, but occasionally, by chance, one grows into an inflationary bubble that becomes a universe. The Wheeler-DeWitt equation is not a complete theory. It assumes a particular form of quantum mechanics and doesn't incorporate all aspects of quantum field theory. But it demonstrates that mathematics allows for spontaneous creation of universes from quantum states. Whether nature actually uses this mechanism remains unknown. Testing these ideas is extraordinarily difficult. The wave function of the universe isn't directly observable. We're inside it, part of it. We see its consequences, the structure of space-time, the distribution of matter, but not the underlying quantum state itself. Yet the implications are clear. The universe's origin might be a quantum event requiring no external trigger. The laws of physics themselves might be sufficient to explain existence. Step back from the details and look at the landscape of theories. Inflation before our bang, cyclic bounces, ekpyrotic collisions, eternal inflation multiverse, Wheeler-DeWitt quantum tunneling, loop quantum gravity bridges. Each theory is different, but they share a common theme. None of them require an absolute beginning. Our bang was a transformation, not a creation. Before it came something else, whether inflationary vacuum, contracting universe, quantum foam, or colliding brains. And before that, possibly something else still. The chain of causation might extend infinitely into the past, with no first cause, no moment of creation, no start to time. This challenges our intuition. We're used to stories with beginnings, birth, creation, first moment. But nature doesn't care about human narrative preferences. If the mathematics says time is eternal, then it's eternal. Alternatively, time might be cyclic or even illusory. Roger Penrose's conformal cyclic cosmology suggests the infinite future of one cosmic era becomes the bang of the next. Time loops back on itself. Julian Barber argues time is an emergent property of changing arrangements, not a fundamental dimension. Different perspectives, but both suggest linear time with a definite start is naive. The philosophical implications are profound. If the universe has no beginning, then asking why it exists becomes strange. It exists because it always has existed in some form. Existence is the default state, not something requiring explanation. Nothingness would require explanation. Why wouldn't quantum changes, vacuum energy, or space-time curvature exist? This reverses the usual framing. We've assumed nothingness is simpler than something, so existence needs justification. But in physics, empty quantum states are highly constrained. True nothingness, no fields, no vacuum energy, no quantum changes, no mathematics, no laws, might be impossible. It might violate consistency requirements we don't fully understand yet. If so, then something has always existed and always will exist. The universe transforms continuously. It goes through phases, expanding, contracting, bouncing, inflating, creating structure, dissipating into radiation, repeating. Each phase looks different, but the underlying reality persists. We find ourselves in an expanding phase, seeded by a hot bang that was itself seeded by cold inflation. Trillions of years from now, dark energy might dominate completely, diluting matter to negligible density. The universe would become cold and empty again. Is that an ending, or just another phase transition preparing the conditions for what comes next? If brains collide, another bang could occur. If quantum tunneling happens, new inflationary bubbles could spawn. If loop quantum gravity is correct, maximum density could trigger a bounce. The universe would continue, just in different form. This picture fits with deeper principles in physics. Energy is conserved. Information might be conserved. Fundamental constants seem constant. Reality has structure and follows rules. Why would that structure suddenly appear from nothing or disappear into nothing? The universe doesn't start or end, it transforms. And that transformation is governed by principles we're gradually uncovering through observation, experiment, and mathematical reasoning. The question shifts from, why is there something rather than nothing, to what determines the form that something takes at any given moment? The answer to what existed before our bang is both simpler and stranger than absolute nothing. There was something, a quantum state, a vacuum field, a contracting universe, a colliding brain, a timeless configuration space. The details remain uncertain. The theory differs between frameworks, but the conclusion is consistent. Nothing in the philosophical sense never existed, and possibly cannot exist. The quantum vacuum won't allow it. The uncertainty principle prevents it. The mathematics forbids it. Reality at its deepest level is not empty. It's not static. It's a dynamic system of fields and probabilities and geometry that never stops evolving. Our bang was one moment in this endless evolution, an important moment for us because it created the conditions for stars, planets, and life. But not a special moment cosmically, just a transition, like water becoming steam, except what transitioned was space-time itself. Modern cosmology has pushed our understanding back beyond the traditional bang to reveal a richer story. We know inflation happened first, driven by vacuum energy. We know the universe might be cyclic, bouncing or colliding through endless eras. We know quantum gravity replaces the singularity with something finite. We know the vacuum contains energy shaping cosmic evolution. What we don't know yet is which theory is correct. Is it ekpyrotic collisions, loop quantum bounces, eternal inflation multiverse, quantum tunneling? Perhaps multiple theories are correct in different regimes. Perhaps they're all approximations of a deeper theory we haven't discovered. Future observations will narrow the possibilities. Better measurements of the cosmic microwave background, detection of primordial gravitational waves, more precise tests of dark energy, advances in quantum gravity theories, experiments pushing to higher energies. Each piece of data constrains which models are viable, but already we know enough to revolutionize how we think about creation. The universe didn't come from nothing, it came from something that transforms, that something has always existed, at least as far as our physics can tell. The question isn't why existence rather than non-existence. The question is why this particular form of existence right now, and the answer involves quantum mechanics, gravity, vacuum energy, inflation, and possibly higher dimensions. It involves mathematics describing how fields evolve, how space-time curves, how probabilities collapse into actuality. It involves natural law, not supernatural intervention, physical process, not metaphysical mystery. The cosmos is not a creation, it's an eternal pattern of change, sometimes expanding, sometimes contracting, sometimes inflating, sometimes bouncing, always transforming, always existing, never truly starting or ending in any absolute sense. We're part of this transformation, temporary arrangements of atoms assembled by the cooling aftermath of one particular bang in one particular region of an infinite multiverse, or one particular cycle of an eternal recurrence. We exist for a brief moment, aware and curious, attempting to understand the larger pattern we're embedded in. And what we've learned is humbling. We're temporary witnesses to an eternal cosmic dance. The universe is far older, far vaster, and far stranger than we imagined. Our bang wasn't the start of everything. It was barely even a start, just one more transition in a reality having no beginning and needing none. Nothing never existed. The void was never empty. Reality is eternal transformation, and we're fortunate enough to witness one brief phase of it. That's what existed before our bang. That's what exists now. That's what will exist forever. Not nothing, everything.